to create lifecycle technology for the digital twin itself, which is quite easily and often overlooked. In the next couple of minutes, I will walk you through what we have identified as general barriers or obstacles that make it hard or impossible for SMEs to create and use digital twins effectively and efficiently in a sustainable way. We find that there are two main types of barriers, namely organizational barriers and technological barriers. Often these are interlinked, and so you will find that we classify the barriers according to the type we feel it belongs to most. And for your understanding, we use the word barriers like we use obstacles or even challenges. Depending on the specific nature and arrangement of a company, it can differ to which extent a barrier will impede or prevent you from being successful in your digital twin ambition. These barriers can lead to serious headaches and do not always prevent us, but rather hinder us from being successful. Of course, this enough hindrance can result in a decision to stop any such activity and miss out on the benefits the digital twin can bring us. Here are the 4 organizational barriers we choose to highlight. They relate to vision and leadership, changes in working practices, having open questions and options, so that is being spoiled with choice, and creating the right synergy between business partners in the value chain and supporting ecosystem. And I'll briefly comment on each. The first is visionary leadership. A lack of clear vision can lead you anywhere, but also everywhere and nowhere. Knowing and supporting your business, which includes colleagues, partners, and customers, means knowing why you are doing what you are doing, and this makes all the difference. Also, electing a champion then to see it through and make it happen will give you an edge. Then changing working practice. Resistance is futile. Okay, there I go with these cliches, but the only thing that is certain is change, and the world is changing. So solution scope crosses the silo borders, and we work better with tangible and measurable benefits. Therefore, be prepared by having clarity about how to work to ensure business continuity. This means realizing that our employees, customers, and partners are quite often a part of the solution. Then, open questions and options. Being able to do everything can lead to doing very little well. Key challenges here include, this is for the organizations and interorganizational, sharing responsibility, ensuring secure access, and also protecting intellectual property, right? We need to focus to keep the plan aligned with the vision and the mission, but remember, you must also remain flexible, because this is also a strength since things change. Then the ecosystem support. There is still much confusion in the market, so who does what, how do we work together, and so on. Generic integrating technologies only make up a small part of the digital twin solution. Then having shared goals can lead to economically viable solutions and encourage innovation, making the customization exercise more effective and efficient. Doing it together can also help avoid that dreaded vendor lock-in and these spaghetti solutions. Next, I'll walk you through the technological barriers we identified pertaining to these 5 aspects. Making sure the solution is fit for its purpose to bring the actual and expected value. Paying attention to the software development and lifecycle management to ensure reliable operation of the digital twin itself. Having the right infrastructure resources available to execute the solution well. Having the IT in place to deal with accountability and uncertainty relating to trust of the system and its results or use. And the technology that brings it all together, providing holistic integration of the data, model, and purpose or process that constitutes this digital twin. Again, I'll go through them for you. fit for purpose. Combining data, models, and purpose, we need to ensure that it continues to remain fit for its intended use. This means we need to make sure that we have IT solutions that give access to the right data that you can trust and gets it where it needs to be on time. On the other side, having a model with the right level of detail is crucial. As we all know the garbage in, garbage out principle of data, this also holds for the model one uses. On top of this, we also need to think about making it future-proof, right? Knowing that the eventual use of the digital twin will not be limited by our present-day expectations. Reliable operation. Maintaining the digital twin during its own life cycle stages is just as important as the life cycle management of the actual system it supports. Thinking of designing, building, deployment of operation, operating, maintaining, decommissioning, and even disposal of this digital twin that you have, or components of your digital twin. Here, maintenance, for example, might also include software upgrades and improvements. So just like a man, no digital twin is an island, and there are other digital twins, systems, and models that are useful or used for perhaps unknown purposes right now. And we need to ensure that our digital twin is interoperable so that it can avoid, or we can avoid eventually ending up with an expensive, obsolete solution. Execution infrastructure. A sufficiently comprehensive digital twin will require extensive computational resources, probably distributed over a hybrid cloud that may combine private clouds and with other vendor platforms. And then you have your HPC resources, high performance computing resources. So when you speak of distributed co-simulation of different kinds of models, synchronized with an actual system state, you require design patterns for efficient use to be effective. Current high-performance computing and cloud-native solutions are not generic enough for the dynamic digital twin application yet. Scaling up with a more powerful machine is not always the scalable way to ensure continued operation. Distributed architectures that ensure the growth and evolution of your system requires careful consideration. And beyond the issue of scale, security is also not always consistent, which means a secured by design solution is needed for a generic approach, as IP and safety are typically critical for the industry domain. Accountability and uncertainty. The digital twin is only as good as the data and simulation and reasoning models in the solution. Data must be cleaned, reconciled, and also become understood by those who wish to inspect them to increase the trustworthiness of the system. Trust is then achieved through the ownership of data, models, and the system itself. Being able to identify who did what, when it was done, and why gives the user means of accountability and gives confidence in the decisions made. Then the wrong decisions or their repetition can also be better avoided. Holistic integration. Developing a digital twin requires understanding the dynamics of the entire system. This is not only more challenging because of the heterogeneous and highly granular compositional nature of this distributed co-simulation model that must integrate efficiently with reasoning logic to address specific purpose or purposes, but it also requires careful design to allow for the integration of multiple stakeholders, users of the digital twin or those who depend on it, and probably different kinds of unexpected purposes. For example, versioning of input data, models, or human interaction to the static parts of a digital twin, that is, to its configuration, requires special attention. And engineering the holistic digital twin means finding low-code solutions, since not every user or developer is a programmer. Automating or semi-automation semi-automating its operation to deal with complicated and complex system aspects, because a single human being can't always know every single aspect about the entire system. And then thirdly, ensuring the interoperability, or that interoperability is thought of in the system design in an attempt to make it compatible with the unexpected or the unknown. So I imagine that these resonate with you in some way or another, depending on what kind of twins you're dealing with. And of course, we could discuss them in much more detail. But for now, I want to thank you for your attention. And I give the floor to Oliver, who will talk about the enabling technologies that in some way or another start to address these challenges. Thank you.
Thank you very much, Paolo. And Oliver, you can start with sharing your screen and you will be automatically a moderator.
Okay, thank you.
Yes, we can hear you, Oliver. That's very good. We can still see Paolo's screen.
Yeah, I'm just trying to share now.
Don't worry. Yes, now it's initiating. We can see your screen now also in presenter mode, so you can go ahead.
Perfect. Okay, thank you for that, Marcella. I'll just introduce myself a little bit. So my name's Oliver Barrowclough. I work at SINTEF as a researcher. SINTEF is in Norway. And today I'm going to be talking about enabling technologies for digital twin. So my background is in mathematics, so I don't have deep expertise on all the technologies that I'm talking about today, but I have had experience of them one way or another through various EU projects that I've worked on over the last several years. So several of these technologies have already been mentioned in the previous presentations from yesterday on common understanding and the demonstrations, and also earlier today. We also heard in the assessment presentation yesterday that SMEs often struggle with digitalization, and that while it's not necessary for them to have a deep technical expertise, it is useful with a basic understanding of what the technologies offer and what the current trends are. So this is what I hope to do in this presentation. So in digital twin, we want to model aspects of a product, a process, or a service, and we want to do this with sufficient accuracy to be able to take decisions for a specific purpose. So this reflects the definition of digital twin that we heard in the presentation on common understanding yesterday. So to achieve this goal, we typically need to combine tools from new technologies like industrial Internet of Things, big data analytics, artificial intelligence, and cloud and edge computing. We need to combine these with the more mature technologies like the computer-aided technologies and product lifecycle management. Even though the computer-aided technologies and product lifecycle management have been around for several decades and we consider them as mature technologies, they're still in a state of constant development and improvement to address new requirements that come from, for example, implementation of digital twin. I should say that digital twins can, of course, include other technologies, such as blockchain, for example. But for the sake of the time we have today, I'm just going to concentrate on these ones as some of the most relevant technologies. It should also be said that these categories are somehow cover the wider scope of digital transformation and not just within the context of digital twin. So let's start by looking at computer-aided technologies and PLM, product lifecycle management. The CAX refers to the three technologies of computer-aided design, computer-aided engineering, and computer-aided manufacturing. So computer-aided design, CAD software, is typically the starting point in product development where the idea gets transformed into a digital model. Most CAD systems today still use boundary representations, which essentially means that, that the interior of the object is, or the object itself is hollow. But there's increasing demand to be able to also model the interior of the object, for example, modeling variable material properties. This is something that's been motivated by the rise of additive manufacturing in the recent years. So modeling the interior of a geometric model requires volumetric representations, which are very much in focus in the research world at the moment and slowly making their way into industrial applications. As part of the design phase, you often want to test how the model performs. This can be done by manufacturing prototypes, but a quicker and more integrated way to do this is to use computer-aided engineering software. So this is software that allows you to simulate how the product will perform under a variety of physical conditions, sometimes also including multi-physics simulations. So based on the results of the simulation, new design iterations can be made. Different modeling paradigms can be used for this. So the most mature and most common approach that's used today is known as finite element modeling. This involves conversions between the design representation and the simulation representation, which is normally a mesh. So these conversions can be time consuming and are also prone to error. For a more recent approach to unify the design and simulation stage is known as isogeometric analysis. This is also tied up with the volumetric representations of CAD. The applications using isogeometric analysis are really still in the sort of early stages of development, but are starting to emerge in industrial applications. The final of the three computer-aided technologies is CAM, computer-aided manufacturing. So this is where the geometric model is converted into machine instructions that determine how to manufacture the object. This is either with a subtractive approach like milling, or can be with an additive approach such as 3D printing. Again, during manufacturing, issues can occur that mean that you have to go back to the design stage and make certain adjustments to make sure that the object is manufacturable. So in going through all these processes, there are often lots of different versions of the model that are created. These different representations have different formats. So in order to have a traceable process, it's important to include proper versioning information of the history of the modeling process. So this is where PLM comes in. PLM covers a wide variety of methods for integrating, storing, and accessing data throughout the product lifetime. The data is not normally limited just to the digital representation of the model itself. It can also include documentation, results of experiments, the relevant process data. So in this way, PLM can provide full traceability of the processes. It can also aid with interoperability by promoting the proper use of standards. And I'll talk a little bit more about that later in the presentation. So one of the more recent types of technologies that's relevant for digital twin is the Internet of Things. Particularly in our setting, what's relevant is the industrial Internet of Things. Internet of Things refers to a system of interrelated, interconnected objects that collect data and transfer it over a network without the need for human interaction. These objects are typically fully automated sensor devices that can be used to monitor the status of a system or from a remote location. In the industrial setting, the situation is similar. It's just that the sensors are often monitoring more sensitive processes, and therefore the sensors often need to be more sensitive themselves. And also in the industrial setting, you have the downstream applications used in industry put more requirements on the formats of the data coming from the sensors. So it becomes more important to use standards. In the context of digital twin, IoT devices are used to deliver real-time digital information about the status of the physical twin or the conditions that it's exposed to. So for a digital twin to receive up-to-date real-time information about the physical twin, there's a need to establish a communication pathway, which typically needs to be fast, it needs to be secure, and it needs to be reliable. So there are a number of communication protocols that exist to do this, including the ones we're all familiar with, such as Wi-Fi and Bluetooth, but there are many, many more. So the emergence of 5G is also an enabler for Internet of Things, providing higher speeds, ultra-low latency, increased network capacity, and increased availability. One example where we can clearly see the use of Internet of Things is in predictive maintenance. By receiving constant updates on the status of a large complex system of machines and analyzing these results, we can obtain more precise information about when maintenance is necessary. This often requires processing and analyzing large amounts of data, which brings us on to the next category of technologies, cloud and edge computing. The cloud and edge computing provide ways to deal with the large amount of data that's streamed from the IoT devices. For SMEs, having and maintaining the latest and greatest computational hardware is expensive, and the hardware often becomes quickly outdated. The cloud computing is really a technology that's arisen from the cost of smaller companies having to invest in their own computational hardware. Computational resources in the cloud are offered as a service, meaning that smaller companies can also afford to make use of state-of-the-art hardware as and when they need it. On the other hand, we have edge computing, which provides distributed computational resources close to where they're needed. In many contexts, this means close to where the data is produced on the edge of the network. So one way of thinking about the difference between cloud and edge computing is that cloud computing operates on big data, whereas edge computing operates on the real-time data that's produced by the sensors. The cloud performs complex computations, finding patterns in large amounts of data, while edge computing solves simpler problems locally, improving response times and saving bandwidth. One example could be the use of video processing sensors for counting items on a production line. On the one hand, you could send the entire video stream back to the cloud for video processing, but hardware for performing such video processing is typically also available on the edge. So by making use of the edge hardware, the counting can be done locally and only the final count is sent back to the server rather than the entire video stream. So this can save, of course, a lot of bandwidth in transferring data. This example shows how industrial Internet of Things and digital twin require more of a combined edge and cloud architecture rather than one based purely on a centralized cloud. So today, a lot of processing happens in the cloud, but as Internet of Things devices are becoming more and more common, there is a trend towards performing more computation on the edge. So this means in the future there'll be less necessity to send all censored data back to the server, and more just the data that matters. The ability to process data on the edge can also have advantages with respect to security and privacy, meaning that personal data can be processed locally and never needs to be sent outside the user's network. Efficient use of edge and cloud resources can also contribute to energy efficiency and cost reductions. One of the key technologies that enables both cloud and edge computing is virtualization. Virtualization is about separating the physical computing hardware into one or more virtual devices. This allows smaller businesses to make use of computational resources without deep knowledge of the hardware, software, and networking. There are, of course, the major providers of cloud services, Amazon and Microsoft, and so on. It is worth noting that a lot of the smaller cloud providers based in Europe can often provide a more tailored approach and one that conforms better to the European data regulations. So even though we have available streams of live data that are fed back to the digital twin, either directly or via cloud computing services. It's not necessarily the case that the data is in a format that's most useful for the purpose of the digital twin. That's to be able to make decisions. Big data is what it says it is. It's about large quantities of data. But this large quantities can be interpreted in different ways, and one common term that's used in big data is the 3 V's: volume, velocity, and variety. So volume refers simply to the amount of data created in terabytes, petabytes, and exabytes. Velocity refers to the speed of the growth of the data, for example, from streaming new data from IoT devices. Variety refers to the multitude of data types that we have to deal with, and also ensuring that the metadata is available that allows the appropriate connections between the different formats. There are many logistical challenges in dealing with big data, ranging from quality assurance, organization and availability, security, and cost. When it comes to quality, if you don't ensure that the data received is of sufficient quality for the specific purpose of the digital twin, then it can be difficult to extract useful information from the large pool of data. Getting access to the data in a format that's suited to the analytics that need to be performed is also important. It's not helpful if the data is stored in closed databases and will take a lot of time or effort to extract. The value in big data is not just that there is a lot of it, or that it's being created at great speed. It comes from being able to analyze the data and reveal underlying patterns, correlations, and trends. It's also important not to have the impression that big data solves everything. It's true that large bodies of data can reveal trends that are not clear from smaller bodies of data, but that doesn't mean that all bodies of large data necessarily contain useful information. So what is useful should normally be motivated from the business decisions, and the data captured for digital twin should be centered around that purpose rather than the way around. Visualization is also important when it comes to analytics. It's about the way the complex data can be translated into something that a human can look at and take decisions quickly. Visualization can be many different things. It can be simple dashboards where the decisions are taken based on looking at graphical data, or they could be more advanced rendering of 3D data that can be used, for example, in augmented or virtual reality. And this is really dependent on the specific application. Artificial intelligence can, in some senses, be considered part of big data analytics. It's often what's used to provide the analytics, but it's a wide enough topic that I think it warrants discussion of its own. Many people think of AI as being the same thing as machine learning, but AI is more of a sort of blanket term that covers many different computational methods. Essentially anything that emulates what we think of as human intelligence. The one example is the computational engine in chess. It's considered an AI, even though it's only performing exhaustive searches of the space of potential moves. This doesn't involve learning, it's simple search of the space of potential moves. But it's still competitive with human intelligence, given enough computational power. But in any case, the main driver of the increase in interest in AI in recent years has been due to machine learning, and in particular deep learning. The deep learning is a subset of machine learning that uses artificial neural networks that can learn a sort of hierarchy of features that can be used to draw conclusions from the data. So we can divide deep learning and machine learning into several classes: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. The supervised learning is about learning from labeled data. The data can be thought of as input-output pairs. So a common example of this is that inputs can be photos of cats and dogs, and the output is simply a label saying whether the photo is of a cat or a dog. So one of the nice properties of supervised learning using deep neural networks is that it can be used to solve problems that were thought to be completely intractable just a few years ago. These are typically tasks that have traditionally been well suited to human intelligence. But now we see many cases where deep neural networks can even outperform humans in these tasks. The idea in supervised learning is that a neural network sees enough of the input-output pairs to be able to use the patterns it learns to infer new outputs from unlabeled inputs entirely independently. The catch here is that you first need a large body of labeled data to be able to perform the training. And this task of labeling is often has to be done manually, and it's a very time-consuming process. The advantage is that this labeling, in principle, only needs to be done once. Then the neural network will learn to mimic the actions of the labelers. So the next is unsupervised learning, and this is about finding patterns in data that hasn't been labeled by humans. So just providing the raw data set and trying to use deep neural networks to determine what the important features of the data set are. In principle, avoiding the manual labeling needed in supervised learning seems appealing. But in practice, unsupervised learning is a lot more difficult to implement in a way that will provide us with useful analytics. So in the cat and dog example, unsupervised learning could maybe tell us in this large data set that there are two categories, but it wouldn't be able to separate them into cats and dogs. It wouldn't be able to give that meaning. So semi-supervised learning is sort of an approach to combine supervised and unsupervised learning. So it can, in some sense, get the best of both worlds. So yeah, we can use large unlabeled data sets to infer general characteristics of the data, and then a smaller labeled set that can fine-tune to the specific task. So this sort of minimizes the number of labels that need to be manually generated while still being able to pull out the features that are only present in the large data sets. The reinforcement learning is quite different in an approach. It can be very powerful. It's more about how agents take actions based on the state of an environment. So the type of agent and environment can be very general, and reinforcement learning is normally most useful for making decisions in dynamic environments. So this is more towards the automation side of digital twins. So AI can be used to solve a wide range of tasks, and which of these methods you choose for a specific problem depends entirely on the requirements of the problem to be solved. So common tasks in AI include object detection and classification, localization, so that's, for example, in an image, putting a bounding box around the object you're looking for. Segmentation is going as far as saying what class each pixel belongs to. You have generative modeling, which can actually generate new data sets based on seeing the characteristics of a large data set. Also clustering and visualization. Clustering is kind of an unsupervised learning, separating a large data set into several different clusters without necessarily knowing what those clusters mean. There are, of course, many privacy and security issues that arise in integrating AI into process chains. So one way to tackle some of these issues is known as federated learning. Federated learning provides a decentralized framework for learning, which utilizes edge devices that it avoids the exchange of private data with the central server. So I've already mentioned a couple of times about standards and how important they are in digital twin. So I'd just like to say a little bit more about how we address this in Change to Twin. Given that the digital twin borrows from many different types of technology, interoperability is really important. is about enabling software, different software and hardware components to talk together. Whatever the constellation of technologies used and for whatever purpose, the key is to tie these technologies together with the use of standards. The benefits of standards are that they reduce the overall complexity of dealing with large systems. They help promote a common understanding of what the data is and what the purpose of the exchange is. And standards also help avoid vendor lock-in, where businesses get tied into using tools from a specific vendor because the digital models get tied up in proprietary formats. In Change to Twin, we have a major focus on the STEP standard, which covers many of the aspects of the computer-aided technologies. But the landscape of standards used in digital twin is, of course, much larger and encompasses much wider types of data than just those covered by STEP. So we're currently working in Change to Twin at mapping out all the standards that are relevant for digital twin, particularly with respect to manufacturing. We interact with these standards to different extents in the project. So some of the most mature standards are just used as they are, whereas some need fine-tuning to the needs of digital twin. So the consortium will be active in standardization bodies, working groups to try to influence the future development of standards that are important for digital twin. So I'd just like to wrap up by mentioning that the Change to Twin consortium covers many of the technologies that I've talked about today, and that we're working to make these technologies available in the Change to Twin marketplace. So you'll hear more about the marketplace in the presentation coming up in the next session. So part of what we're doing is about translating these individual technologies into a more complete digital twin solutions, and this is where the pilot experiments and the experiments from the open calls will be important. So we're currently in the stage of mapping out the technologies we have available in the consortium and identifying any gaps, which can potentially be filled by external providers. We've had a lot of interest already from external providers to get their technologies listed in the marketplace. So I think that's everything I wanted to say today. I'm of course happy to answer any questions, and thank you for your attention.
Thank you very much, Oliver. And now we'll just try to see if Florence and her audio is working again.
Do you hear me?
Yes, we can hear you, Florence.
Great.
The floor is yours.
Thank you, Paolo. Thank you, Oliver, for your both presentation. Maybe someone has questions for both of our presenters. Do you have some questions?
I have a question, Giuseppe Padula, that I'm part. So good afternoon to all the team, and it's great. I mean, very interesting organization. My congratulations. I have the following question that is concerning the standard. So there are of course different organizations and different ways for the standardization. I am talking, for instance, to other standardization process that are taking part, for instance, in USA. Now, the question is how much this standardization process should be focused on, let's say, on our European market, or how much it should be as much as wider possible with a cross confrontation on this. I mean, on these other other standards that are under development.
So yeah, I think I'm not the expert on standards, but from my point of view, it is very important that these are international standards. I think if they're just available to the European community, then they're less likely to become adopted as general standards. So I mean, the wider the standards are, the wider the adoption will be. So I think it's very important to be part of the international standards community. Like STEP, for example, this is of course an international standard.
Yeah, thanks, Oliver.
Has anyone a question regarding barriers to digital twin adoptions or regarding the enabling technology presented? No, it seems we do not have questions, so it was very clear. If you have